This is going to be a bit more down to earth, like talking about concrete, small problems, and not like trying to solve intelligence, whatever that means. Yeah, and then I want to start with actually with animals and humans. So we know for a long time. Well, I mean, perhaps we've known that for forever, but we know, like, as a science field, that animals and humans can learn quite complex behaviors by basically associating actions with outcomes. And now, what outcomes here might be debated, and there are like various approaches. But at least we can say that reward and punishment are important drives of such learning. And well, this goes back at least to the 50s with famous psychologists like Skinner, on the one hand, representing here the extreme behaviorist approach. And I want to show you a short movie of how you can train a pigeon to play ping pong. So the way you do that is
the two pigeons are...
So you put the ball, and you see that the two pigeons are playing against each other. And the way they're trained is that if one pigeon is able to score, that, like, to pass the ball through the other one's gate, it gets a bit of food. So everything here is like, you give them reward if they succeed. So you see if the pigeon succeeds, they get a bit of reward, and they actually can play quite well this stupid little game. And this is not exactly natural pigeon behavior, right? And still they can learn it quite good. While this is playing, so let me remind you or tell you, if you don't know, that this extreme behaviorists, they say, well, the only thing you have to learn is associate your actions with your stimulus with action. So it's direct stimulus-response association and nothing beyond that. So you don't need any kind of mental representation or anything going. So all you care about is behavior. Now the stimulus maps to behavior exactly. Now, about the same time, there were other people, also kind of behaviorists, but a bit less extreme, and they said, no, you actually need some kind of inner representation. You need something. So back then, the term, one of the terms that were coined is a cognitive map. So you need some kind of representation of the world that lets you actually plan things ahead and do it like kind of a mental stimulation. So let's see an example for that. So yeah, can you please play the second video? So in this kind of experiments, what you do is you put rats in kind of a maze. Well, there is sound, but I will speak instead of it. And you let it learn the way to where the food is. And it does this by trial and error, just like the pigeons before. But there is only one way it can go to get the food. And then the trick is, we'll say it shortly, that
well, it also appears to recheck the layout before using the route it's learned.
Yeah. Well, I don't know if you saw it already, but the trick is that after that you open, like this. You change the structure of the maze. You open two other ways that the rat never took before, and then you ask the rat what you want to do now. And then you can see that the rat, although it never took the shortest way that is only now opened, she knows on the first trial to go through this shortest path to get the food.
And he does it the very first time.
And then, like, the idea was that you need to have some kind of a map or like representation of the environment that will let you plan and do that when you have new tasks to solve. Okay, so what I want you to take from this slide is that what we learn and how we do that, it's quite complex. And we up until today, we don't have like clear answers to what exactly and how exactly this kind of learning works. And probably there is more than one answer. I mean, probably there is truth to both of these stories, right? So, yeah, this doesn't work. So maybe you can swap the slides for now. Or, sorry. So I will tell you, while it's running, that what we do in the lab, no, it doesn't work. So what we do in the lab is we build computational models to try and explain this kind of learning and decision-making in all sorts of tasks. So the first question is, okay, why do you do that? I mean, don't you have something better to do with your time? And the things about this kind of model building is, so I want to give you like 3 reasons to why it's good to build computational models. So what do you mean by computational model? I mean, we build models that are mathematical and like have computational principles to try to explain this kind of phenomena of learning and behavior and decision making. So a first reason is that building this kind of models, it lets us explain and analyze behavior better. So I told you and I showed you that there are all kinds of questions of how we learn and what are the mechanisms. And if we have like a framework or a computational model, we can perhaps analyze the data better and explain it and draw conclusions. The second reason, which is also important and it's been like very influential, and I'm not going to talk about it at all after this point, is that if we have a computational model, we can use it as kind of to explain how the brain actually solves this. Okay, so going beyond behavior and talks about the neurocomputation mechanism underlying this kind of learning, decision making, and behavior. And this, again, this has been influential, but I'm not going to talk about this in my talk. And then the third point, which is more related to today's theme, is that perhaps we can use inspiration, or actually or perhaps even the algorithm, who knows, that animals and humans use to solve this kind of tasks, and take and use them for building sophisticated artificial agents. And I'm going to, and this is more or less where I am with my research, or perhaps somewhere in the middle, and this is more or less what I'm going to talk about. So to do that, we need a model, okay? And I want to present you, like, very briefly on a very high level, a formal model for reinforcement learning. Okay, so reinforcement learning is, you can think about it as kind of an operant learning. And the idea is that there is an ongoing interaction between an agent, which, so previously the agent was the pigeon, right, or the rat, and the environment. And what happens is that the agent chooses some action, so you know, the rat can choose where to go or something like that, or the pigeon can choose how to move its beak, I don't know. And then the environment transfers you to the next state and gives you a reward signal. And this is all there is to it. And from this you have to learn. And what do you have to learn? You have to learn a good mapping of states to action. So you have to learn a good policy that will guarantee that you get a lot of reward in the end. All right? And so here's an example. This is not a pigeon playing, and it's not a rat. It's a relatively little neural network, just like Aaron talked about, like the same kind of networks. And it's playing this breakout thing, right? So a state here is just the frame of the image, where the ball is, where the paddle is, how many bricks you're left. And the actions you can choose, like to move the paddle to the left, move the paddle to the right, and your reward, you're getting a point of reward every time you break a brick, right? And your goal is to break as many bricks as you can. Okay, so as a side comment, usually there are some mathematical assumptions about the process, and it's not important for us in the talk, but just remember this sounds very general. In principle it is, but the methods that we have today rely on some extra assumptions that I'm not going to get into. So, okay, we know what the goal is. The goal is to learn how to behave, which will, in a way that will guarantee that we get a lot of reward. And then the action is how are we going to do that? And now I want to present three major ways to do that. So a first way is just, okay, find someone who knows how to solve the task. Okay, find yourself an expert, and then just learn to imitate him. Okay, so watch him closely, and then. So, for example, you know, when I was a kid, I used to sit next to my cousin playing some computer games, I don't know, Prince of Persia and stuff like this that were popular back then. And, you know, I was sitting and watching, and finally, when it was my turn to play, I already knew quite a lot about the game, right? So this is like an imitation learning in its basic form. And it's basically kind of a supervised learning. So you try to learn from a teacher how to behave. And this has lots of problems and issues, but maybe an obvious one is, okay, what if I don't have anyone to know how to solve the task, right? What if I don't have an expert? Even if you do have an expert, there are some other issues that I'm not going to get into, but just know that this is not a perfect solution anyway. The next idea is, okay, if I know how the world works, I can just plan ahead, and I can use something that is similar to the cognitive map, right? So if I know that if I move with the previous one, if I know that if I will move right, the ball will fall, and so on, and I can plan ahead, I can just find the optimal policy. So here is another example. You have to find a good route I don't know, a space vehicle from the here on Mars to here on Mars, and there are some hills in the way, and you want to minimize energy consumption. And then there are clever algorithms that let you like compute shortest path between points, even though it sounds hard. I mean, if you think about, perhaps today it sounds trivial because we have all this navigation assistance, but you can do this stuff for other tasks other than navigation. And then the final approach, which we started with, is more or less actually reinforcement learning, and this just means you're going to learn by trial and error, by reward and punishment. And this is just a fancy way to say, try some stuff around and reinforce what works. Okay, so we're just going to try a lot of stuff, and whatever was successful, you're going to try again. This is basically the whole idea. So there are many ways to do that, and there are all kind of delicate issues, but remember, this is like a very simple-minded learning rule, right? So you're just going to try things, and whatever worked, you keep trying it, and maybe improving it a little bit. So here's an example. Well, it turned out that this is exactly the game that the pigeons played, right? So this is Pong, and this little thing here is controlled, again, by a tiny neural network. And you can see that by just giving him, just like we gave the pigeon, a score every time that it scored, like a 1 point of reward, like food. So here we give it, it's more abstract, we give it reward, and it learns to play. But this is actually literally the same game, right? So we can do it not only with pigeons. So now I'm going to tell you a little bit about what I did in this field of reinforcement learning. And I've been working on the exploration problem. So what is the exploration problem? So I told you that the way we're going to do that is to find a policy is just we're going to try stuff around and then reinforce what worked. But for that, you need to actually try stuff around, right? And then there is this tension known as in the literature as the exploration-exploitation dilemma. And basically what it means is that, well, if you want to find a good policy and you want to maximize reward, you want to keep doing the successful stuff, right? You found something that works, you want to keep doing it. But then what if there are like other good options that you never tried and you don't know that they're aware? So you all decided to come here today and hear about science, but perhaps in the bar next door they serve this amazing beer that you don't know about, and you should explore this instead, right? Not suggesting that you should, but. So you have somehow to balance this tension of exploration and exploitation. And here's a simple example. So suppose you are this little dot and you start here, but you don't know the structure of this world, right? You only know where you are. And then you can move to each of the direction. And like the good thing to do is to go over all the way and get the big reward, which you cannot see, but this is like plus 10. But you can find easily the going to the left and get a small reward, and then every time you will go right, you will probably fall off the bridge because you don't know to keep going right, and you will think that going right is very bad because you did not explore this option good enough. And you will stick going to the left, which is suboptimal. It's not the good thing to do. So the questions that we asked in the research, like our research question is what are the good ways to actually optimize the exploration? So I'm not going to talk about the balancing of exploration and exploitation. We did that. I mean, we did something on that as well. But I'm going to focus on, OK, we decided that we want to explore. How are we going to do that? And now, let's start with some simple ideas. So, let's try start with what we want. We want our exploration to focus on useful parts of the environment, right? So if there are places that we know that are very bad, we don't actually need to know how bad they are. We're not going to choose them in the later anyway. And we also want exploration, well, this is the whole point, to reduce our uncertainty, right? So we want to explore stuff that we don't know about enough yet. And now, the first option that people actually use, I mean, it's not a complete straw man, is to say, OK, every once in a while, I'm going to choose a random action. Okay, so I'm going to behave more or less according to what I think is best, but from time to time, I'll allow myself to like try something at random and go with this. And this is obviously very bad because, or can be at least highly inefficient, because if you choose actions at random, you're not directing your exploration to get you new knowledge. You might waste exploration resources on stuff that you know very well. So here is another example. You start in this upper left corner, and the world is this very big grid world. You don't see the tiles, but every state is a small box. And if you do basically a random walk, then your chances of getting out of the first room is basically very close to zero. I mean, it will take you much it will take you a great amount of time to actually get out of the first room. Another idea that people suggested is, okay, let's do something a bit more sophisticated and try to count. Okay, so for each action or state, we're going to count how many times I took it, and then I'm going to use this counter as a measure of how well I explored it already. And the intuition here is that if there is an action or an option that I chose like a little number of times, perhaps it's worth to explore more. And I want to suggest that this is better, of course, but it still doesn't really solve the problem. Because why? Because the counters provide you very local information and they ignore long-term consequences. So long-term consequences are something we know from our daily life, and I want to emphasize and to convince you that it's also important in these limited settings of like controlled behavior here. So consider again this example. So say that you took the action left and the action right the same number of times. Okay, 10 times. So the counter alone cannot differentiate between them. So it tells you you should explore them like evenly likely. But clearly, we want to invest more exploration in the right action because it leads you to much more potential states. And the counter alone does not know that. So what we want is not really a counter, but a measure that tells us how good an action or a state for exploration is based on the long-term consequences and not just on the immediate outcomes. So this is very similar to what happens in standard reinforcement learning. So one way to learn these good policies that I mentioned before is to learn something called a value function. And we denote this in Q as a Q function. And what this function measures is if I'm now at a given place, a state, and I'm taking some action, how much reward I'm going to get from now until infinity. So not just the immediate reward, but how I'm going to get in the future. And this is the thing I want to maximize. And in our work, what we did, and like Aaron said, you can read the paper if you like. So we constructed a value function for exploration. So the idea is that we have this E value, which will tell us how much new knowledge I'm going to gain if I'm now in state S and taking state action A, and not just the immediate outcome, not just the immediate new knowledge, which we can measure more or less with a counter, but the future knowledge, in some sense of the word knowledge that I'm probably not going to define here because it's a bit technical. Right, I will skip this for the interest of time, and I will just show you some results. So we named the algorithm Dora the Explorer, which is just aptly named. And it has some reason, but really the reason is that we can write Dora. And then, like, one point that I want to make, even though I did not tell you the algorithm itself, which is a bit technical, is that this learning of E-values is basically the same kind of learning that we do on a regular basis in reinforcement learning. And then this allows us to use the same techniques, and modern reinforcement learning has very powerful techniques, or relatively powerful techniques, to learn this kind of value functions. And we can use the same techniques to learn the E-values, basically. So we can do this in big, complicated problems. So here is an example. This is actually our network after it was trained on this game in which you play this poor chicken that has to cross the road without being turned into a schnitzel. And so this is like the idea. This is an old Atari game. Some of you probably played it. And this is after the network was trained, so I hope that you can see that it actually managed to run without being hit by the cars. And this is the learning curve. So in black, it's our algorithm, and you can see that it learns, well, I wouldn't say fast, because it takes millions of steps, and this is related to Aaron's talk. I'm not going to elaborate on that, but at least it beats the competition, so hooray. Right, so just in few words, what I'm working on right now, this idea of the E-values, the previous algorithm, it was more or less heuristic. So we try to think what we would like from an exploration, and then we try to come up with some idea that somehow maps to these intuitions. So now we're trying to work on something that is more like derived from principles, and perhaps establish a theory of, or a small theory at least, of optimal exploration, which is independent of reward. So up until now, there was always reward in the picture, right? But we know that animals are curious, so it's hard to explain just pure curiosity without external reward with the standard models. So we are not the first to ask this question, but we're trying to go into this part now. And so here is example from the first environments that I showed you. So again, you start here, but this time the trajectories that I show you, they're not being sampled from a uniform random distribution policies. They're being sampled from what we call an optimal exploration policy, and you can see that it well travels the whole 4 rooms much more efficiently. Right, and we hope that maybe such approach, which will enable us to close back the loop and go back to ask questions about animal behavior and exploration, but we're still not there quite right, but perhaps, well, I hope. So to sum up, I hope that I was able to convince you, to some level at least, that studying computational models of learning and behavior is interesting and perhaps an important thing to do, and that artificial agents can learn and perform quite complex tasks, at least like if you give them one task to solve, they can learn that from what is ultimately very simple ideas of reward and punishment, and that's it. Well, as a side note, it doesn't mean that they don't form complex inner representation as a result of this learning, but this is perhaps too delicate to discuss right now. And then the exploration is a crucial thing for this kind of learning, obviously, because if you are going to learn from your own experience, you have to have your experience diverse enough and sample enough options from the states so you can learn from them. And long-term consequences matter, and they matter not only for reward, they matter also for information, or for gathering information and for exploration. This is like the thing that we worked about. And then I want to comment on the whole theme of the evening and relate to who talked before me, that I think that building like truly autonomous behaving agents, this kind of learning will not be enough, and probably you need to combine all sorts of types of learning. So think about how we learn things, or how animals learn things. So we imitate others, we plan, we use mental stimulation, we learn habits, like in a kind of associating stimulus to responses. We have all kind of stuff, and crucially, I think, and I mean, we are like embedded in a world, and we don't just solve one task that in a computer simulation and that's it. So we have very rich world, and we are inside some environment, we have a body. So I think these are like really important issues, and they relate to reinforcement learning, but of course we cannot discuss everything in one short talk. So with that, I want to thank you and thank Libby and Shir, who gave me the opportunity to talk here, and I'll be happy to answer questions.
Thank you. So we have questions from the audience. Udi.
Back to your program, one thing that I found very interesting is that unlike the pigeons, your program was sort of rotating or moving all the time.
Batting around, yeah.
Like Muhammad Ali trying to, and I was wondering if there's a reason for this and if you can elaborate on that.
Yeah, so first of all, this is not my own program, but okay, sure. Yeah, so it has, I have two explanations, basically. So the first one is that action selection in this model is inherently stochastic, and actually, if it would collapse to a deterministic policy, it could not learn anymore or anything, so you expect it to be noisy a bit. But then the more deep reason is that, let's go back to this. Yeah, this one, right? Yeah, so when the ball is far away, it actually doesn't matter which action you take. It really doesn't matter. I mean, well, you move because think about, well, maybe the network learns the value function, okay? Supposedly the network learns the value function. No, the value function, the queue of going up and for going down is the same. And then your action selection function is going to be stochastic. And then you just have this noise. But note that when it needs to move to hit the ball, it's very like precise, right? But when it doesn't matter, so the action selection is just going to be like at random because it doesn't know anything else. There is no cost on moving here. Perhaps you can reduce this by inducing some other terms like, don't jitter around and stuff like this. But
it's more difficult for the other player, right?
The other player it's hard-coded, and it's a fixed policy, very simple, yeah.
Any more questions? So I will ask a question about the balance between exploring or staying in the same place and getting the reward that is in this place, which is something I think is, in a way, is also difficult for us as humans. So is the algorithm knows how to find this balance himself, or is it very specific to the problem?
Yeah, this is a good and a hard question. The algorithm doesn't know on itself, not exactly. So usually the way you train these things is you have some parameter controlling the level of exploratoriness, okay? And then you start with high exploration and you reduce it down. So this is controlled by the teacher in some sense. But there are other ways to do that, and yeah, so it really depends on the problem, but we don't have like a closed solution. We did not solve this problem. So people have solved this problem in very simple tasks that don't have long-term consequences. So if you're familiar with what is called a multi-armed bandit task, so you just have to pick again and again from the same number of alternatives. So there we know we have all the theory that you like, it's super fancy, and we know the optimal things to do. But in this like more complex cases, we don't really. And yeah.
Coming soon.
Probably not.
Okay, so let's thank Lior. Thank you again.